So here is our unit on linear algebra, where we'll be studying mostly a thing called a matrice. So to start off, we review something that you've done back in grade 10 and grade 11. What is a linear equation? Y equals mx plus b, or in standard form, ax plus by plus c equals 0. And a system of linear equations is when you have more than one of these and more than one thing that's unknown. So for example, here's two equations and two unknowns. What value of x and y makes both of them true? Do you remember ways that you could solve this? You could use substitution. Substitution was one method, elimination was another method. Yes. Those are the two that we learned, and we're going to learn some more this year. Okay, substitution would mean, can you get a variable by itself? Now, if I were using substitution for this equations, which this should be, is it an equal sign? Did I fix it on yours? No. No, it should be an equal sign there. Otherwise, that doesn't make any sense. But if I were to solve this, I would look and say, which variable is the easiest to get by itself? It's not a variable. But yes, the 6 is by itself. No. But at this point, you could get the x by itself, and then you could go to the other equation and plug in, instead of x, you could plug in the 6 minus 4y. That creates an equation with only one variable that you don't know, and we just use our algebra to figure things out. So 12 minus 8y minus 3y equals 1. Negative 11y equals negative 11. And y is equal to 1. Then once you have found what one of the variables is, you could plug that value back into this equation and find out that x equals 2. Sometimes when you did this back in grade 10 and grade 11, you wrote your solution as a coordinate, because if you were to graph both of those lines would intersect at the coordinate 2, 1. So this was the substitution technique that you learned in the past. The elimination technique, that's where you lined up your equations, and what you tried to do was, me personally, I like to get the coefficients the same, but one positive, one negative. So for example, if I took all of equation 1 and I multiplied it by a negative 2, can you see that equation 1 would become negative 2x minus 8y equals negative 12. And then if I rewrote equation 2 underneath, 2x minus 3y equals 1, the elimination technique says once you've done that and everything lines up like terms, you could just add those two equations together. And sure enough, the negative 2x and 2x cancel out, get eliminated. Negative 8y minus 3y would become negative 11y, and negative 12 plus 1 would become negative 11. And you get y equals 1 that way as well. Oh, it should be the same answer. Okay? So this idea will form a basis for solving later on. There we go. So we talked about this before. If I were to graph both of those lines, then where they intersect would be the solution. Now there are three, if we are going to categorize and imagine two lines, there are three types of solutions. One independent solution is what we saw in our first example. Two lines with different slopes are going to cross. If they have different slopes and different y-intercepts, they're going to cross, and there's only going to be one solution. You can draw a picture of that. So if I have different slopes, that's important. Different y-intercepts, if I have one or the other, does it happen? No. You need different slopes. Because what happens if you have the same slope? They might be parallel, and then they may not cross. They could have the same y-intercept, right?
If it's the same y-intercept and same slope, it's an infinite solution.
Yeah. So technically in this one, they could have the same y-intercept. As long as they have different slopes, they're going to cross at a point. If they have the same y-intercept and different slopes, well, then you know that the y-intercept is the only point where they're going to cross. A second system is a dependent system. This is where you have one line here, the other line here, and they're identical. The two equations may not appear to be identical when you first look at them, right? But when you simplify them, they are the same. Like y equals 2x plus 6 is the same line as 2y equals 4y plus 12. What did I, oh, no, easy. There we go. What did I do? I just multiplied them or divided 1 by 2. And they're the same equation, but they look different, right? We're getting used to seeing this in math, right? Two things that look different that are equal to each other. Fractions, 2/3 and 4/6. Look different, but are the same thing.
Great. A 0 is the same as 100, right?
Yeah.
Okay.
Okay? So they'll have the same slope and the same y-intercept. And anytime you have the same slope and the same point, they're going to be exactly the same line. We call that a dependent system because there's an infinite amount of solutions. If you try to solve these, okay, you get some interesting facts. For example, if I tried to use substitution here, y is equal to 2x plus 6, and I didn't recognize that they were the same. And this sometimes happens. You get into your modes of using substitution or elimination to solve things, and you're like, oh, well, I just have to plug in 2x plus 6 for y. What's going to happen? You get 4x plus 12 equals 4x plus 12. And you solve for x, so you move, and you're like, oh my goodness. 0 is equal to 0. And you're like, wow. Okay? When is that not true? It's always true. Okay? And because it's always true, you get this infinite solutions. If you were to do elimination with something like this, you'll get a similar thing, like 0 equals 0 plus 0. Ooh, always true. Which leads us to our last system, which is an incompatible system. This is where you have two lines in 2 dimensions that are parallel, and so they'll never intersect. So what does that look like? Here's y equals 2x plus 6 and y equals 2x plus 3. If you use the elimination technique here, let's say I subtract these equations, I get 0, 0, plus 3, and you get something that seems a little bit off. When is 0 equal to 3?
Never.
Yeah, well, I'm sure we could be creative here. When is 0 equal to 3? I don't know. Like I've got good stories. Like I got a card once in the mail that said this. What was the card for?
Oh, I think I know.
You think you know?
Yeah.
Want to enlighten us?
Well, if you have two people have it without protection, you have
It was a baby announcement. Yeah.
Peter, why would you say it in that way? What would you say has a kid without protection?
Yes.
I know that.
This is
Because what's a bad
Okay.
joke I read that was like 1 + 1 is.
oh. All right. So choose a technique of your liking
None of them.
and solve. And these first two that you're going to do on your own, well, the first one you're going to do on your own is just straightforward. Here, we've got a little bit of thinking to do, and then we'll move into, well, that one's still 2 dimensions. Do I have a 3-dimension one? Yes.
Dun, dun, dun.
So now we're talking about lines in 3 dimensions. Okay? But we'll start off with an easy one for you.